we need to know the type of reaction because that's going to determine the mechanism. So when you look at this, we're starting with an alkene. It doesn't matter if it's a cycloalkene or just an alkene. As long as you have a double bond, then you're looking at what's over the arrow or under the arrow, the reactants and the solvents. So when we look at this, if you look at your flashcards or you look at your notes, you have HBr and then peroxides and light. You might not always see the light. It might just say peroxide or H2O2. So when you see HBr and peroxide, that's free radical bromination. Alright, so for this, I'm just going to put the type just so if we need to go back and identify, we can. This was the one that I think most people requested to go through. Free radical bromination, so radicals are different. We're not dealing with carbocations, we're dealing with an odd number of electrons. When we look at the mechanism, all we're going to worry about for the mechanism is the propagation step. So when we're looking at the mechanism, all we're worrying about is the propagation. We're not worrying about initiation. So remember the initiation step starts, that's why we need the peroxide, and it uses one of the HBRs, and it forms this bromine radical. So bromine radical actually has 7 electrons around it. It's not bonded. It doesn't have a formal charge because bromine has 7 valence electrons. And so for this radical, there's an odd number of electrons. When there's odd number, that's kind of the definition of a radical. This is what's formed in that initiation step. Every single time we're forming that radical. When we look at the mechanism, we're worrying about the propagation step. So we're starting with the bromine radical, and we're going to start with, in this case, the cycloalkene, which is this. So within this free radical bromination, right, the first step of propagation is actually somehow getting rid of that single electron. Because these radicals are very reactive. They have that single electron, and so it's going to be reactive. Now, these free radical bromination mechanisms, this is where we're using the half arrow. All right, so if you're like curving it, it's a half arrow. Represents a single electron. I know it looks weird, but it just shows you it's a single electron and not 2 electrons. And so what's going to happen, let me change colors here. One of the electrons from bromine, so I'll kind of draw it down here, all right, single electron, and one of the electrons in this double bond. All right, a bond is always 2 electrons. So one of the electrons in this double bond are going to come together. 2 electrons coming together is going to form a bond. Now, free radical bromination, if you look at the considerations, or you just kind of look at your flashcards, this is an anti-Markovnikov, right, anti-Markovnikov, which means that bromine adds to the less substituted carbon on the alkene, which means bromine is actually going to add here. So, I'll try to stick to my different colors. We still have 1 electron here that's kind of just sitting there. This other electron from this double bond is going to actually go to the other carbon. So we actually have 3 single arrows in this first step. 3 single electrons. So we have 1 from the bromine, we have 1 from the double bond, and then the other one from the double bond is going to this carbon. So this is kind of like carbocations. Radicals want to form the most stable, which is most substituted radical, which means the radical is that single electron. So the single electron is going to be on the more substituted carbon of the alkene. And so if we draw the resulting product here, so that single dot represents a single electron. Now again, technically this carbon doesn't have a formal charge because carbon has 4 valence electrons, and right now that carbon has 4 electrons around it. You're thinking about drawing the circle for formal charge, 1, 2, 3, 4. But we shouldn't see a radical as a final product. So now we need to use that electron somehow. And so then remember that HBr, we have lots of HBr. So we have as much HBr as we need. Now we're going to use up this single electron again. As we use up that single electron, this half arrow, we're going to have one of the electrons from this bond meeting it. Now it doesn't matter which way the head of your arrow points. Mine probably is different from what I wrote down than what I wrote up here. As long as you only have half of the head of the arrow, you're good. So one of the electrons from this bond will meet this electron. That's going to form a bond to the hydrogen. And now this other electron is going to go back to the bromine. So we're going to continue to have that bromine radical until we terminate this process. And the very last step is the termination. What we are concerned about is this propagation step. How are we actually forming the organic product? And so if we take a look at what this product is, so we have the methyl groups that we had initially, bromine added to the less substituted carbon of the alkene, which was here. A hydrogen, right, was added here. You don't need to show that hydrogen, but just know that that is where the hydrogen was added. And then you technically have that Br radical, right, still have this Br radical, but that's a side product. You don't have to worry about putting it. If it asks for the product of this reaction, it wants the organic product. So it wants this cyclohexane. And so with this, again, free radical bromination, you're looking at HBr and peroxides. Peroxide is the key thing there because the peroxide is what allows the initiation step with the HBr to occur because hydrogen peroxide is unstable. But this free radical bromination, your halogen, so your bromine adds anti-Markovnikov. So the bromine adds to the less substituted carbon. Hydrogen adds to the more substituted carbon. And that's how we get that organic product for free radical bromination. Questions on this mechanism? It does look weird with those half arrows, right? And kind of the idea of the single electrons moving. But this is the only one that we have those single electrons as they go through. All right, so the second one, we're looking at the whole mechanism again. So the first thing that we always have to do, and this is why the flashcards are useful, is we have to make sure we know the type of reaction that's occurring. Because just like the notes are split between Markovnikov and anti-Markovnikov, some reactions also have carbocations, some do not. And so when you take a look, again, your starting product, we're not worried about what that is in terms of the type of reaction as long as it's an alkene, which it is. But then when you look at your arrow, you have H2SO4 and H2O. So H2SO4, sulfuric acid, and so strong acid, and then water. So over the arrow we have a strong acid, under the arrow we have H2O. Now I do want to just make a note for this reaction. This could be any strong acid that does not include a halogen. So it cannot be HCl, it cannot be HBr, cannot be HI, because then you're getting into a different type of alkene reaction. So for this, we typically see H2SO4, or we might see HNO3. Those are usually the two that we see with this type of reaction. So we have an acid, and we have water. So if you think about the types of reactions here, we have acid, catalyzed, and then we have water, so addition of water. This is actually one of the first reactions that we learned. So if we take a look at this reaction with acid-catalyzed addition of water, so the catalyst is the acid. So the acid is kind of what starts this reaction. You could draw this out like we've drawn before, where we did H, and then we did O, SO3H. We wrote it out like this before just to actually show how the electrons are moving to the hydrogen and then, it goes back to the oxygen. Or if you want to just show the electrons going to one of the H's and you just kind of show them moving over, that's okay as well. But this really allows you to see what's actually happening. So we start with the acid catalyzing this reaction. So the electrons that are in this double bond are going to attack the hydrogen, and then the electrons that are in this bond between the H and the O are going back to the oxygen. So one of our side products here is HSO4-. We're removing the H+, the first acidic hydrogen from H2SO4. We do that. Now, acid-catalyzed addition of water. This is a Markovnikov reaction. So if it's Markovnikov, that means that your substituent is adding to the more substituted carbon because this creates a carbocation. We always want the most stable carbocation. So if we're looking at creating a carbocation here, carbocation is going to form on the more substituted side, which means the hydrogen's coming down here. All right, so there's where the hydrogen went. There already was another hydrogen there. This is just the hydrogen that came from the acid. And now this carbon only has 3 bonds. There's the carbocation. You always want to do a quick check. Is this the most stable carbocation? This carbon has 1, 2, 3 things attached. The tertiary. It's already the most stable carbocation that we could have. And so then we're looking at, all right, well now how do we get rid of that carbocation? Well, we've catalyzed this reaction with the acid. Now we have the solvent, which is water. I'm just going to draw H2O like this. You could draw it out like the Lewis structure if you want. I'm just going to kind of use this shorthand. So water has the electrons, right, the lone pairs on the oxygen. So one of these lone pairs is going to attack that carbocation. Carbocation is positive, lone pairs are partially negative, and so that's going to attack the positive carbocation. I'm just using all kinds of colors here. All right, once that oxygen, those lone pairs attack that carbocation, now it creates a bond. I'm going to drop the hydrogen over here. We know that there's hydrogens there. So it didn't disappear, it didn't get used up. I'm just, bond line structures, we don't show the hydrogens. But now here, we've added O and 2 H's. One of the lone pairs was used to create this bond, so this still has another lone pair. When oxygen has 3 bonds, it has a positive formal charge. Oxygen, if it wants a formal charge of, or if it has a formal charge of 0, has 2 lone pairs and 2 bonds. And so now this has a positive formal charge. We do not want a positive formal charge. And our final product should never have formal charge. We always have water. Water is the solvent. So this is always surrounded with water. And so what we can do, because the goal is to get this oxygen back to a formal charge of 0, which means it should have 2 bonds and 2 lone pairs. So this oxygen can attack one of the hydrogens. Does it matter what hydrogen? No. Could attack the top one or the bottom one. It doesn't matter, just like it doesn't matter which lone pair you pick. But then these lone pairs are going to go back to the oxygen. And when it goes back to the oxygen, now we just have this OH group. And then another side product is H3O+, but we are not concerned about these side products that we get. So if you look at this, right, with the mechanism, we can see how it works. But if you look, the OH from the water attaches Markovnikov. It attaches to the more substituted carbon. Well, then this third one doesn't require a mechanism. This is hydroboration-oxidation. OH, you do not have to worry about the mechanism. OH adds to the less substituted side. Yep, hydroboration-oxidation.